Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're looking at a new section referred to as polycyclic, polynuclear fused ring, or condensed ring aromatic compounds. These are compounds based on aromatics such as benzene, except they have multiple benzenes attached to each other, such as in the examples I've provided on screen here. If you have two benzene molecules fused together in a side-to-side fashion as drawn here, you have the molecule referred to as naphthalene. If there are three attached side to side, you have the molecule referred to as anthracene. Phenanthrene is three aromatic benzene type units attached in a slightly different fashion. Now, polycyclic fused compounds like these listed here tend to be quite carcinogenic. One of the most carcinogenic compounds is this molecule, which consists of many fused benzene-like rings. This molecule is referred to as benz alpha pyrene. Sometimes also called 1,2-benzpyrene. Now, benz alpha pyrene is a very carcinogenic polycyclic aromatic compound. It is found and produced in the combustion of organic matter. It will be found in coal, fuel oil, cigarettes, forest fires, and roasting meats. Now, what's interesting is when you deal with these polycyclics, and I want to focus now on naphthalene, anthracene, and phenanthrene. So we'll remove this. You should note that with regards to nomenclature of these polycyclics, they often have fixed numbering schemes. So, we'll often find numbering schemes such as this: 1, 2, 3, 4, 5, 6, 7, 8 for naphthalene. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for anthracene, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for phenanthrene. So unlike the numbering in benzene or other cyclohexanes, which starts at the position of a substituent, polycyclic number systems are fixed by convention. Now you have to be somewhat cautious with this. Let's look at benzene, for example. Benzene's numbering starts at the substituent. So if I have a chloro here, I have 1 chlorobenzene. If I put the chloro here, because it's the exact same molecule, it is also 1 chlorobenzene. In some ways, this type of nomenclature does hold true for naphthalene. Let's take a look at naphthalene. If I have the chlorine here, I have 1 chloro-naphthalene. If, however, the chlorine is here, because this is a chemically different environment, it has a different name. And I don't start counting from the chloro. In benzene, you would always start counting a chloro. This is fixed as number 2. So this is 2 chloro-naphthalene. Now, one of the things that you have to keep in mind, however, is that if we go back to the 1-chloro, if I keep this in mind, how would I name a molecule that has the chloro in this position? Or how would I name the molecule if I had the chloro say in this position? Is this guy 8-chloro? Is this guy 5-chloro? Well, if you actually compare the structures of 1-chloro-naphthalene to what you might call 8-chloro-naphthalene and 5-chloro-naphthalene, well, they're the same structure. All I've done is taken this flat ring and I flipped it. If I flip it this way, then I get this molecule. And if I flip it this way and then that way, I get this molecule. In other words, all three drawings are the same molecule. It's just flipped. And if you want to check this out, you can build a molecular model and examine it. Because of this, they're all 1-chloro-naphthalene. So watch for symmetry causing similarity in the compound. Because the two compounds are the same, they're all referred to as 1-chloro-naphthalene. Now, if you have an alcohol group, the IUPAC nomenclature for the alcohol is based on replacing the allene ending and adding all. And so this would be referred to as 2-naphthol. 2-naphthol. However, in common nomenclature, we actually designate positions using Greek letters. We've seen this used in aldehydes and ketones. It turns out that there is a fixed Greek letter number system. Let's use black for that, where the positions are designated as follows. Since there's symmetry and you can flip the molecule, a single substitution in this position, or this position, or this position, or this position leads to the same molecule, and so they're referred to as alpha positions. Substitution in this position, or this one, or this one, because you can flip the structure, produces the same thing, so it's referred to as beta. In here, the OH is in the beta position, so this is referred to as beta naphthol, naming it as an alkyl. Beta naphthol alcohol. 2 words. Beta naphthol alcohol would be the common name. Okay. All right, let's move on and now take a quick look at the bonding in naphthalene. Bonding in naphthalene. Right. Naphthalene and other polycyclics are aromatic. If you take the time to take a look at the pi system, you will determine that each carbon atom is sp squared hybridized. As such, each ring is flat, and The fused ring system contains a Huckel number of electrons. 4n plus 2 equals pi. Solve for n. N is an integer. In this case, we have 2, 4, 6, 8, 10 pi electrons. 4n plus 2 equals 10. You solve for that, n equals 2. So these are aromatic molecules. Now, suppose I want to draw the resonance structures for naphthalene and compare those to benzene. So I'm going to draw some resonance structures, and what I can do in the first case, of course, is I can rotate the ring on here. If I do that, I get this resonance contributor. And if I rotated this ring, I'd get this resonance contributor. If I rotated it this way on the other ring, I'd get this. If you look carefully at these structures, you will notice that the pi bonds occupy very different positions in every structure's case. Now compare this to benzene. Remember in the case of benzene? In the case of benzene, if I drew benzene's resonance structures, the two major contributors I would get would look like this. In essence, these two resonance contributors are identical. If I picked any fixed bonding position, I'd find in one structure, between the two X's, there's no double bond character. If I look between the two X's in the next structure, there's double bond character. If I do that for every bond, I find that happens. 50% of the time you have a double bond character, and the other 50% of the time you don't. If I superimpose these two structures and draw the resonance hybrid, I draw something with a circle in the middle indicating complete delocalization of the pi bond. That is, the pi bond's not very alkene-like. Pi electrons are delocalized, and the resonance hybrid is a better representation of the true nature of the benzene structure. I guess what we're really saying is that this molecule, which I might refer to as 1,3,5 cyclohexatriene, does not exist. And that's much more like the delocalized structure. Well, the fact that naphthalene is aromatic, like benzene, does that mean it's also better to draw it as the resonance hybrid, where we don't show localized pi bonds? Is it better to represent naphthalene, like benzene, with the little circles in the middle? Well, we would agree with the fact that none of these resonance contributors actually exist. What exists is the resonance hybrid. But is the bonding of naphthalene as delocalized as that is in the case of benzene? Well, to answer that question, let's look at positions 1 and 2. I'm going to actually label positions 1, 2, and 3 because we'll want to look at 2, 3 afterwards. So here's 1, 2, and 3. Now look at the carbon bond I've labeled as 1, 2. And tell me how many structures have a double bond between position 1 and 2. Out of the 3 resonance contributors, position 1, 2 has a double bond 2 times out of 3. If they all make the equal contribution to the resonance hybrid, then each would make 1/3. That is, between carbons 1 and 2, you have double bond character 2/3 of the time. Or C12 would have 67% double bond character. Now look at position 2 and 3. Okay, so position 1, 2, if I say C1 to C2, 67% alkene-like. Now let's look at positions 2 and 3. Well, position 2 and 3 has double bond in only one structure. If I go to C2, C3, That would suggest only 33% of the time do I get alkene-like behavior. Now, if this theoretical model held true, since double bonds give you shorter bonds, we should be able to see this in the actual structure. If I look at an X-ray crystallographic determination of the structure for naphthalene, I get some interesting carbon-carbon distances. I'm going to just put a couple up. The carbon-carbon distance between carbons 1 and carbon 2 is 1.36 angstroms. The determined carbon-carbon distance between carbons 2 and 3 is 1.40 angstroms. It is a longer bond. And this lengthening corresponds to the expected value of the smaller percentage of alkene character. Well, what does this all say? In summary then, unlike benzene, where everything's half and half, and there's total delocalization of the pi electrons, in the case of naphthalene, some double bond character is more localized in certain positions than in other positions. Some double bond character is located to a greater extent between carbons 1 and 2 than carbons 2 and 3. What this means is naphthalene is less delocalized and more alkene-like in certain bonds, and is better represented by drawing double bonds, such as we've done here, than by drawing the resonance hybrid. This is more like the true structure of naphthalene. Well, does this apply in all cases? What if we look at another polycyclic? Why don't we try drawing the resonance contributors for the molecule phenanthrene? So I'll begin. Here is phenanthrene. And we can put our double bonds like this. So suppose I started with this system and I said, let's take a look at all possible resonance contributors. What is the first thing I could do? Well, one of the first things I could do is rotate. You can clearly see I could rotate the pi bonds in this ring, thusly. So I'll do that. Take the arrows out, because if I leave the arrows in, keep putting arrows in, it'll get really confusing. So I'm going to draw a new phenanthrene where I rotated the pi bonds in the upper right ring. So this stays. And we rotate those pi bonds. Great. All right. So I've rotated that pi bond. What else can I do? Well, I certainly could rotate this pi bond in this structure, so I can do that. So if I rotate the bonds in the left ring, I get this. There we go. Now, you know what? You wouldn't spot this necessarily, but if you think about it, you notice it's true. I could rotate this upper right ring again. Won't that give me the same thing I started with it? Let's try and see. Okay. So we'll keep this one the same. Now let's rotate this guy again. Well, if I rotate that, well, don't I generate the one? Because that's where we rotated first time. And indeed, that ring is the same. But notice I have the ring in that position with this ring in a different. The pi electrons here are different than those. And so if resonance structures are moving pi electrons to different positions, each of these structures has the pi electrons in a slightly different position when you look at the whole molecule. And remember that with resonance structures, you've got to look at the whole molecule. Yes, this ring and this ring have their electrons arranged the same, but this ring and this ring are different. That means overall the two molecules represent two different resonance structures. Okay. So what we're going to do now is take a close look at our possibilities, and I'm going to look at this structure because this structure is the one that gives me the fifth possibility. And see, whether I have bonds like this or bonds like that, it's the same thing. They're both saying the same thing. No matter which side I put the pi bond, it means this between those two carbons, there is a pi bond. And I can rotate those pi electrons in the middle ring from that resonance structure. So if we do that, we end up with pi bond here, pi bond here, get pi bond here, pi bond here, pi bond here, and we have pi bond here and pi bond here. Now, we can generate then 5 different resonance contributors for the molecule phenanthrene. Because there's more fused rings, we get more resonance contributors. Now, what is the effect if we focus on some carbon-carbon double bonds with regards to localization of pi electrons? Is it totally delocalized like benzene? Was naphthalene just a glitch? Or is the effect we've seen in naphthalene increasing because we have even more fused rings? Well, I want you to focus specifically at position 9, 10. If you remember our numbering scheme, take a look at positions 9 and 10. 9, 10. For emphasis, 9, 10. Someone make them stop. 9, 10. Okay, so carbon 9, carbon 10. And look at all the resonance contributors that have double bond character. Double bond here, double bond here, double bond here, double bond here. Only this structure, resonance contributor, has no double bond character. That's 4 out of 5. That's 80% double bond character. This molecule has so much double bond character, one would think that that double bond in position 910 is extremely localized, almost like a completely pure alkene. In fact, it is so completely localized that you can do reactions you normally can't do with aromatics. Because of the increased localization, we can hit this molecule with reagents that would react with alkenes, but not with aromatic rings. For example, Br2. Br2 with aromatics, you had to use the catalyst FeBr3 unless the aromatic was very activated. In this case, you just use Br2, and you will get transaddition of bromine. You'll get a Br here, down, and a Br up. You get transaddition of the bromine. What if I use KMNO4, cold dilute? Another reagent used in alkenes. KMNO4, base, cold dilute. This produced cis addition of OHs, a 1,2-diol. And in this case, we'd get that addition at the 9-10 position because there's so much alkene-like character. But doesn't that disrupt aromaticity? Isn't that extremely unfavorable? Note that the aromatic rings, 2 of them are retained. And so while the total delocalization of aromaticity might somewhat be disrupted, the aromaticity of 2 separate rings is retained, and so overall there's no net loss of aromaticity. So looking at it from the viewpoint of aromaticity, there's no net loss in this reaction. Plus the fact with regards to delocalization, this is a very localized alkene-like bond. Everything in this reaction looks good. Now this leads us to a major conclusion about polycyclics with regards to their chemical reactivity. What is that? Polycyclics, because of more localization of the alkenes and the fact that you can retain aromatic rings and still react, tend to be more reactive than their benzene counterparts. Let's look at this with regards to the reactivity of naphthalene and look at some specific examples. Then we'll add in a few molecules of Anthracene Phenanthrene as well. Let's start with oxidation reactions. Oxidation. It turns out that unlike benzene, which is very hard to oxidize, naphthalene is more easily oxidized. We can react naphthalene with a vanadium divanadium pentoxide, air, and heat. Hit it with heat. And we can oxidize this molecule to phthalic acid. Of course, if there's sufficient heat around, the phthalic acid will quickly cyclize in the presence of continued heating, losing H2O. Will produce phthalic anhydride. Phthalic anhydride. So phthalic acid can convert to phthalic anhydride. Now, what's really interesting is we can do even milder oxidations. For example, I can take CrO3 in acetic acid, apply some heat, and I can make a 22% yield of this molecule. A 1,4-naphthylquinone. A 1,4-naphthylquinone. Notice that the positions that get oxidized are those that allow for the maximal retention of aromaticity. Or, if you like, the bonds that tend to be most alkene-like. And it doesn't matter which acid you use. If I use, for example, anthracene, so here is an anthracene. If I take anthracene with CrO3, H2SO4, and heat, I could get 9,10-anthraquinone. This really shows quite nicely the retention of aromaticity in the two side rings. Anthraquinone. So 9,10 anthraquinone. Likewise, you can do this reaction on phenanthrene. Remembering that the most alkene-like bond is the 9,10 bond, CrO3, H2SO4, and heat. Well, that will produce, of course, in the 9,10 position, double bond O's. Again, the most alkene-like bond gets oxidized, and you still retain significant aromaticity, hence giving you 9,10 phenanthraquinone. And you can get up to 48% yield of this. So oxidation chemistry works fairly well with these polycyclics. What about reduction? What happens if we take a look at reduction reactions? Reductions. Well, remember the case of benzene? To reduce benzene, you need very harsh conditions. You need metal, hydrogen gas, metals such as platinum, nickel, palladium. You needed very high pressures, 350 atmospheres, 300 degrees Celsius, to hydrogenate benzene to cyclohexane. If you threw in something like sodium and ethanol, and a little bit of heat, not much happens. You get really no reaction. And nor would you expect to, because if you remember, ethanol could react with two sodiums excuse me, to give you sodium ethoxide, C2H5O minus Na plus sodium hydride, Na plus H minus. And the sodium hydride, being such a powerful reducing agent, could react with the H plus on the oxygen that you'd get H2 gal, you get another C2H5O minus, sodium plus, and this time you'd get H2 gas. The H minus of the NaH will grab the H plus off the ethanol. If you add this up, overall the reaction is 2C2H5OH plus 2 sodiums. Notice that the sodium hydride will cancel with the sodium hydride. This sodium hydride here cancels with that sodium hydride on the opposite side of the equation. And that gives me 2C2H5 O minus Na plus H2 gas. Now, what you're seeing is that, therefore, that when you throw in sodium and ethanol in the presence of benzene, a little bit of heat, all you're doing is getting sodium methoxide and some H2 gas. H2 gas is not enough to hydrogenate benzene. But what happens if you react naphthalene? If you react naphthalene, with that reagent, sodium, C2H5OH, heat, what do you get? You hydrogenate one of the fused rings. You produce the molecule tetralin. Why would this hydrogenation work? Why would, under mild conditions, H2 gas add to an aromatic ring? Well, one of the most important reasons is that aromaticity is not disrupted. One aromatic ring is retained. Hence, we're just adding H2 gas across a double bond. This can also be seen in the case of the reaction of anthracene. In the case of anthracene, the same reaction with sodium ethanol. Sodium ethanol and heat. Same reaction with sodium ethanol and heat produces 9,10-dihydroanthracene, where the 9,10 position has been hydrogenated. Why would that position be hydrogenated? Why would the 9,10 position be the position that gets hydrogenated? Because hydrogenating the 9,10 position here and here retains two aromatic rings. And so we produce 9,10 dihydroanthracene. Okay. So hydrogenation of these polycyclics occurs more easily as long as an aromatic ring is retained. But what happens if you attempt to hydrogenate such an aromatic ring completely? Remember, benzene to form cyclohexane required very harsh conditions: platinum, hydrogen, 350 atmospheres, 300 degrees Celsius. You find if you try to do complete hydrogenation, that is, you take naphthalene and you react it with 5 H2 gas molecules. Or you take tetralin and you react it with 3 H2 gas molecules. Just enough hydrogen to hydrogenate everything. Nothing happens unless you throw in a catalyst like platinum. You add 225 degrees Celsius and you use 350 atmospheres pressure of that hydrogen. only then will you convert to the molecule decalin, which is the completely hydrogenated version of naphthalene. So in terms of reactivity, we see that these polycyclics tend to be more reactive than benzene when an aromatic ring is retained. But if you're going to try and completely disrupt the aromaticity, then you have the same behavior as you got in the case of benzene. That behavior being the requirement of very harsh conditions. However, oxidation reduction reactions certainly are not the major pathway of reaction for aromatic compounds. We do want to point out that these molecules are aromatic. And as such, do you recall the major reaction path of aromatic benzene? Benzene was observed to react with electrophiles because it had this electron-rich pi cloud. So it was an electrophilic attack. Now, it wasn't just any old electrophile, though. Remember, the aromaticity meant that to overcome the aromaticity, you had to hit with a very powerful electrophile. And so we were doing electrophilic aromatic, but unlike alkenes, which added electrophiles, even a powerful electrophile could only temporarily disrupt the aromaticity. We'd then lose a hydrogen, and because of that, we ended up substituting the electrophile for an H, and so this was called electrophilic aromatic substitution. Electrophilic aromatic substitution was the main reaction path observed for benzene. Well, we'll discover that this path is also a major reaction path for polycyclics. And so in the next Scribblecast lecture, we're going to visit electrophilic aromatic substitution of these fused ring polycyclic aromatic compounds. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.